All right, well, the first sort of important thing to start having in the back of your mind is exam 1 is a week from today. And I'm going to make that over all the lectures, so covers all the material up through today. So the stuff that we talk about on Thursday and Friday, that's not going to be on this exam. That'll be on the next one. So you have time to look back over your stuff. I'm going to, in the assignments for the next 1, 2, 3 days, I'm going to include assignments to go back and look back over those problems, understand the problems you've already done. So I'll give you some basically studying time in your homework assignments. So the best way to get ready for these problems for the exam is to make sure that you understand all the homework problems. The exam questions are going to be based heavily on those homework problems. Okay, they're not going to be the same problems like they are in the quiz, but they're going to be based on those ideas. So I think, to me, here's the thing to ask yourself about those questions. Could you explain how you did that problem to someone else? Can you explain why you made a decision that this should be negative, this should be positive, you should use this equation and stuff? Because it's not going to be the exact same question, but it's going to be based on that same reasoning. All of the solutions to the homework assignments are posted up through the last quiz. So you can go back and compare your solutions to my solutions. And if you did something wrong, you can see where it is. But you need to, it's not enough to just have done those problems once or tried those problems once. You have to go back and make sure that you did them right to be ready for this exam. Okay? Everyone understand what I'm talking about there? Okay. So the solutions to the homework problems, they're posted. I don't know, who's seen those in D2L? Have you? Okay. So yeah, they're posted just alongside where the homework assignments are. Not the ones up for this Friday's quiz, but those will be posted after the quiz on Friday. So you'll have all those solutions to help you get ready. All right. So we've been talking about kinematics of particles along a line, and we're moving on to the last topic, the last area of that topic. So this is the last subject in kinematics of particles along a line. And this is called relative motion. Okay, so as we've been talking about kinematics of particles, one of the key ideas is that you can't put a number to the location of an object, to any type of motion of an object, until you've chosen where to set down a ruler. You know, not a real ruler, but you know what I mean. Like, so you need to choose where your zero position is, and you need to choose what direction you're going to associate with positive and what direction you're going to associate with negative. So remember, you can't put numbers to a particle's location until you choose a ruler, and that means choosing a 0 position and a positive direction. So now we're going to talk about the possibility that there are two different rulers. So what if motion is specified according to two different rulers? We're going to do this with the positive directions in the same direction. So we're not going to worry about changing directions, but we are going to talk about two different choices of 0 position. So the positive directions of these two rulers will be assumed to match. And the question is, what's the relationship between the measurements according to one 0 position and the measurements according to the other? Okay. So can we come up with mathematical expressions for the motion according to one ruler in terms of the motion according to the other ruler? This is going to be an important idea in physics because we're going to see that when we get to kinetics and start talking about forces, the laws of physics that we're going to use to define forces are only valid for certain choices of 0 positions. Okay? And so if we have a different choice of 0 position, we'd like a way to correct that into a choice where the laws of physics hold. Let me draw a picture of what I'm talking about first, and then I'll mention like a couple of cases where you might see this. Okay, so there's one ruler. The 0 position of this one, let's say this is ruler A, and its positive direction is like that, and the negative is like that. And then you have a second ruler. I'll call it 0 position B. Its positive and negative directions match the first one. And both of these are used to track the motion of a particle P as it travels along a line. So you can see in this example, according to ruler A, the position of this particle at this instant is, well, I don't know, we don't have any numbers on this, but let's say -3 inches, whereas the position according to this ruler B, it's -30 inches or something like that. Okay. You understand what I'm talking about? Fascinated? You drawn in? Yeah? I see that enthusiasm. Okay. So when would this be, like when would you want to do this? An example would be like if you're trying to do physics of things that are happening in, like on some kind of, on a space shuttle or something. You're tracking the motion of objects based on cameras that are mounted to the space shuttle, okay? But, and you can think of as that camera as being a coordinate, as being like placing your ruler down. So you're taking the measurements according to the space shuttle, but those measurements by themselves will not satisfy the laws of physics, because that's not and we'll talk about why later, but that's not an acceptable choice of a zero position for the laws of physics to hold. So instead, you'll take those measurements from inside the space shuttle, and then you'll take what you know about the motion of the space shuttle compared to a zero position where the laws of physics do hold, and you'll make that translation from your measurements back to what the measurements would be in an acceptable zero position. Okay, that wasn't super clear, but we'll do some examples that I hope will make it more clear. Okay, so first we have to do a couple of definitions. So let's call the position of particle P according to ruler A. We'll denote that as P for position, and then P for particle, and then like fraction bar over A. Okay, so this P is for position. This is the object that you're tracking, P for particle, and A is the ruler. And when you're talking about this, you'd say position of P relative to A. And then the position of P according to ruler B you'd write that as position of P over B. The P over A and P over B are subscripts. And you'd say position of P relative to B. Okay, so with those definitions, so this is the position of particle P that you would measure with that A ruler, and this is the position of particle B that you'd measure with that B ruler. The relationship between these two measurements is the position of P relative to A is equal to the position of P relative to B plus the position of B relative to A. where P, B relative to A is the position of the zero of ruler B measured by ruler A. And you'd say this the same as you would say the positions of the particles. This would be the position of B relative to A.
So up there, is it that's the place? Is it? Oh no.
Okay. And to remember the order of this, this isn't mathematically, like, it doesn't make mathematical sense in any way. It's just a mnemonic device, a memory device. But to remember the order, think of fraction multiplication. P over A is equal to P over B times B over A. Okay. If you order these correctly in this equation, in the relative motion equation, the subscripts need to work out as fraction multiplication. Any questions about what I'm talking about? All right, so this is the first relative motion equation. The other two come from just taking time derivatives of both sides. So I'll call this equation 1. So the other two relative motion equations come from taking d dt of both sides of equation 1. And so if you take time derivatives of all of these, well, what do you get if you take a time derivative of a position? You get a velocity. And so the second relative motion equation says the velocity of velocity of P relative to A is equal to the velocity of P relative to B plus the velocity of B relative to A. And take another time derivative, and you get that the acceleration of P relative to A is equal to the acceleration of P relative to B plus the acceleration of B relative to A. So notice that relative motion equations 2 and 3 allow for the rulers to be moving relative to each other. Okay, so let's do a couple examples. All right, so so think about those walkways at the airport. You ever been to the airport? It's where the airplanes are. Not the sky. There's also airplanes there, but this is where the airplanes are when they're on the ground. You can read about airports on the internet. But at the airport in Minneapolis, they have these moving walkways. So let's say that the airport walkway moves 3 meters per second. And let's say that a person who's late for their flight has the ability to run at 8 meters per second. So a late passenger can run 8 meters per second. Let me word this a little differently. So let's say that a security guard is, I spelled that wrong, didn't I? Is that UA? Okay, so a security guard on the ground measures the person's speed. What's that measurement? Okay, so before we start thinking carefully about the subscripts and everything, if the passenger is running in the same direction as the moving walkway. Okay, so first of all, if you're late for a flight, don't ever get on the moving walkway going the opposite direction. That won't help. So, okay, so the person's on the moving walkway, going in the same direction that they're running. So just intuitively, what's the measurement going to be on the ground? Yep.
11 meters.
That's right. So you're going to get on that moving walkway. You're going to run 8 meters per second, and those two speeds are going to piggyback on each other, and you're going to go extra fast, right? I mean, you know that sort of from experience. So now let's think about how it works with the subscripts and everything. Okay, so there are some times when your intuition about physics stuff is kind of going to lead you astray, and we have to fix it. This is one where your intuition is just right. But we have to fit it to these equations so that when we go on to more complicated problems, you know how to use these equations, because you won't have good intuition about it when it gets more complicated. So, okay, think about, so you have a ruler that's on the ground, and you have a ruler that's on the walkway. And each of those are taking separate measurements of the motion. What would be, okay, so which of these three equations do we want? There's a position one, a velocity one, and an acceleration one. We want the velocity one, because that's all we're dealing with is velocities. So we want to figure out, well, let me say it this way. How would you label the 3 meters per second? What velocity is that? The velocity of what relative to what? That's the velocity of, like, the moving ruler, the velocity of the walkway relative to the ground. That's a good way to say it. Okay, so velocity of the walkway relative to the ground is 3 meters per second. how would you describe the velocity of the 8 meters per second, how fast the person is capable of running? What would that be in this problem?
Velocity of passenger related to the ground.
Actually, yeah, that's the velocity of the passenger relative to their ground, which is the walkway. You know what I mean? So that's the velocity of the runner, I'll say, relative to the walkway is 8 meters per second. And now we can set up an equation that has these three in it. Well, the one that we want, we're trying to figure out the velocity that would be measured by somebody on the ground. So we want to figure out the velocity of the runner with respect to the ground. Okay, so is there a way we can put these three into a relative motion equation so that that fraction multiplication, you get the cancellations and it makes sense? Well, this one works. You could try out all three if it doesn't occur to you right away. But you know that that fraction multiplication has to work with whatever your final version is. So velocity of the runner relative to the ground is equal to the velocity of the runner relative to the walkway plus the velocity of the walkway relative to the ground. So that is 8 meters per second plus 3 meters per second, 11 meters per second. Any questions about that? Okay. Let's do another one. So this is one where you might have correct intuition about this, or it might be a little hazy. So okay, let's say that this time a passenger is on an elevator. It's accelerating upward at 1 meter per second squared at the instant the passenger drops an object. This exciting event of dropping an object is viewed by a camera on the elevator, okay? And the question is, what's the observed acceleration according to the camera? According to that camera, what does it look like the acceleration of the object is? Okay, so first of all, does anyone happen to have, does an answer jump out to anyone? Yeah?
10.81 meters per second.
Yep, that's right. Yep. So let's go through the calculation of how you do this with the relative motion equations. So okay, let's think of the things that we know. Well, we know something about dropped objects. As long as an object isn't touching any surrounding things, and we don't have any reason to believe air resistance is important, we know that there's an acceleration of 9.81 meters per second squared down. Okay, so we're going to use that value, like we use it in any free fall problem. So how would you label that? Okay, one step back. There's a position, velocity, and acceleration relative motion equation. Which one of those three is going to matter in this case? Acceleration. Okay, so the 9.81, what are we going to call that? And let's say negative 9.81, because we'll choose our positive direction up. Okay, so we know that the acceleration of the object is negative 9.81 meters per second squared according to something. According to what? According to the ground. So when we're using that negative 9.81 meters per second squared, we're always assuming ground. And now what about that 1 meter per second squared? First of all, is that positive or negative? It's positive because we chose our positive direction up. So 1 meter per second squared. And what is that the acceleration of, and what's it relative to? That's right. That's the acceleration of the elevator relative to the ground. And finally, what are we trying to calculate? That's right. We're trying to calculate the acceleration of the object relative to the elevator. And so now we have to set up these three in an equation so that that fraction multiplication works. So this one works. Acceleration of the object relative to the ground is equal to the acceleration of the object relative to the elevator plus the acceleration of the elevator relative to the ground. So object relative to the ground is negative 9.81. Acceleration of the object relative to the elevator, we're going to solve for that. And acceleration of the elevator relative to the ground is positive 1 meter per second squared. So now it's an algebra problem. You're just solving for acceleration of the object relative to the elevator. And you get negative 10.81 meters per second squared. So to the camera, it looks like the acceleration is greater than free fall. Any questions about that process? Okay.
Was this assuming that it had just started? Because the elevator had started and then you dropped the object, would it have the upward momentum like the elevator?
Okay, so when you drop something, once something goes into free fall, so here's what you can do to an object, like Well, this is something that we're going to get into with Newton's laws, but you can think of like all an object wants to maintain is its velocity. If you don't do anything else to an object, all it has is the velocity that it had before. So no matter what your acceleration is when you let go of an object, that object only remembers the velocity that you put into it. So if it accelerates up and you let go of it while it's accelerating up, and you let go of it with at the instant that the elevator has a velocity going up of 2 meters per second, the effect is that object starts by going 2 meters per second, but it immediately, as soon as you let go of it, starts accelerating according to gravity. So you can't give it any acceleration once. It doesn't remember any acceleration once it leaves your hand. It only remembers velocity. Okay. That was sort of a convoluted way to say it, but yeah, I think that's not a bad way to think of it. Like, an object's memory is only velocity. An object doesn't have a memory of acceleration. Okay. Any other questions about that problem? When you do these problems, I really want you to be careful about the labeling and stuff. I know that you could figure out how to do this in your head or whatever, but I want you to get in this habit because we're going to go on to more complicated problems when we start doing things with vectors, and it would be harder to do it in your head, and that habit of doing it in your head would hold you back later on. Okay, so that's why I want you to be careful about the labeling, writing out the equations, that kind of stuff. All right. So here's an example for you to work on. A swimmer jumps into a moving river as the school's swimming coach secretly watches from the woods. No, this isn't going anywhere bad. From his hiding place. Okay, he's trying to figure out if he wants to try to get this person on the team or not, you know. He only has so much energy to commit to recruiting. The coach measures the swimmer moving 1 meter per second east relative to the ground. Okay. So he does that compared to by timing how long the swimmer goes from one tree to another tree. Swimming coach is smart. Then the swimming coach measures the speed of the water at 2 meters per second west. The question is, how fast would the swimmer be in a pool? Okay, So is the coach going to waste his limited illegal recruiting budget on this swimmer? Okay, so work together on this. The key is not the answer, okay? The key is setting up the equations right. So go ahead and, okay, so what do we know? So this is east, we'll call that positive. This is west, we'll call that negative. So the 1 meter per second, the speed that the coach measures the swimmer moving, what are we going to label that? So positive 1 meter per second. We're doing velocities. So what are going to be the subscripts for that? Yep, that's right. Swimmer relative to the ground. And then the 2 meters per second, that's west. So that's going to be negative. What are the labels for that? River, ground. And then what are we trying to calculate? Yep, we want to calculate the velocity of the swimmer relative to the river. And you can arrange these three into the equation. Velocity of the swimmer relative to the ground is equal to the velocity of the swimmer relative to the river plus the velocity of the river relative to the ground. Swimmer relative to the ground is plus 1 meter per second. Swimmer relative to the river is what we're trying to calculate. River relative to the ground is negative 2 meters per second. And so you get that the velocity of the swimmer relative to the river, which is a measure of the person's swimming ability, because all you can do is propel yourself relative to the water, is positive 3 meters per second, which is a little over 6 miles an hour, which I think is pretty fast, actually.
So does the swimming coach recruit him?
I think so, but I'd have to check. I think that's pretty good. Yeah, I think that's pretty good. I should have done more research on swimming speeds. Okay, let's do one more example. So an airplane moves through the air with an acceleration of 9.81 meters per second squared down. I'll talk more about that in a second. It sounds bad for the passengers, but just bear with me for now. What is the observed acceleration of a dropped object on the plane? Yep.
Is the airplane accelerating downward because of gravity?
You know, so that is that is a good question. It could be, but not necessarily. It could be sort of simulating, it could be using its engines to produce this acceleration. I'll talk more about that in a second, okay? But for now, you just go through the relative motion equations to figure out what an object in free fall would look like to the passengers on the plane, okay? Go. So, we're dealing with accelerations. So we know that we're given that the plane has a downward acceleration of 9.81. Let's say that let's choose our positive direction up. So that the plane's acceleration of 9.81 meters per second squared down, what are the subscripts for that? Plane relative to ground, yep. What do we know about an object in free fall? So an object that's dropped on the plane. What? Yeah. So what are the subscripts for that? That's right. So that one's always relative to ground. So a object relative to the ground. And the one that we're trying to find is the acceleration observed on the plane. So the acceleration of the plane, the acceleration of the object relative to the plane. That's what we're trying to find. So we need to arrange these so that fraction multiplication works. Acceleration of the object with respect to the ground is equal to the acceleration of the object with respect to the plane plus the acceleration of the plane relative to the ground. So object relative to ground, that's negative 9.81. Object relative to the plane, that's what we're trying to calculate. Acceleration of the plane relative to the ground is negative 9.81. Rearrange and you get that the acceleration, the observed acceleration on the plane of objects in free fall is 0. So objects have apparent weightlessness. So when they're trying to get astronauts ready for to get away from, well, actually, they don't get away from the Earth's gravity, but they have to deal with the weightlessness of orbit. The way they train them is they put them on airplanes and make the airplanes travel with an acceleration of 9.81 meters per second squared down. And so then astronauts get used to this feeling of weightlessness. So what does it take for a plane so what are the ways that you could make a plane accelerate downwards 9.81? One is to get up really high and drop it. That's not a very safe way to do it. That's right. Yep. So there would be air resistance as it starts getting faster. Yep.
The way they do it, they angle it slightly, and the engine's pushing it down, so that the downward thrust is 9.81.
Yeah. So they can do it. What happens? So what's the path of an object? This isn't something we've talked about yet because this is in 2 and 3 dimensions. But what path does an object follow if you ignore air resistance and you like shoot it out of a gun or a cannon or launch it or whatever. Yeah, it follows a parabolic shape. And so once the thing is launched, even when it's going up, it has an upward velocity, its acceleration is still 9.81 meters per second squared down. So you could actually start an airplane angling up and use the engines to counteract the air resistance and have it travel the path that an object would travel after being launched if there was no air resistance. And through that whole flight, even the whole part where it's going up, the acceleration is 9.81 meters per second squared down. Okay, so you can do this whole path that's much safer than starting up high and dive bombing, and that whole time there's apparent weightlessness inside the plane. Any questions about that problem? Okay. So that's the last topic in particle kinematics along a line. And so now we're going to go from talking about motion along a line, where we've built up some of these ideas, and we're going to extend those ideas to dealing in 2 and 3 dimensions. So now we're moving from kinematics of particles along a line to kinematics of particles in 2 dimensions. And 2 dimensions means we're going to deal with motions in a plane, not an airplane. All right, so before we introduce this new mathematical thing of vector, which is what we're going to need to use vectors to talk about motion in 2 dimensions. Let's think about how we represented direction for particles moving along a line. So motion along a line is an example. It's not the only example, actually, but it's an example of one-dimensional motion. And one-dimensional motion has this requirement. At any instant, the object being tracked only can move in it only has 2 possible choices for direction. You can think of it as forward and back. And so this idea that at any instant the motion can only be positive or negative, it lends itself really nicely to representing direction using the sign. And that's what we did with motion along a line. So therefore, direction could be represented by the sign. Like, for example, you could say the positive direction is forward, negative direction is backward, Okay, so here's the particle. It can only go this way or that way. And that's true of any one-dimensional motion. It doesn't have to be along a line. It's also one-dimensional if you have like a bead sliding along a wire, you know. Even though that wire moves in a two-dimensional space or even a three-dimensional space, at any instant the bead can only go forward or backward. Okay, so now let's think about two-dimensional motion. The positive negative sign isn't enough to specify a direction anymore. Because now at any instant the object has infinitely many choices. Infinitely many choices of direction. So if this is the object and it's free to move in 2D space, it could go this way, this way, you know, infinitely many choices. So the objects, let's change that to quantities. That were represented by signed numbers along a line. Okay, so they're going to have to be represented differently. What are those quantities, before I finish this? What are the quantities that have signs, that have direction, that we dealt with kinematics along a line? Yep, and one other one. Position, yep. So position, velocity, and acceleration. Now they need a different mathematical representation. And that new representation is vectors. So all of these things that were signed numbers, signed numeric values in 1D along a line are going to be vector quantities in 2D. Okay, so what's a vector? I'm glad you asked. A vector is a mathematical object with two properties. The first one is magnitude, and the second one is direction. You can think of it as an arrow. Think of it as an arrow in space. So you can think of that as a vector, where its magnitude is represented by its length. and its direction is represented by, where it's pointing. And you can do math with vectors as follows. And I'm first going to talk about how to do, like, what it means geometrically to add vectors and multiply vectors by a number. And then we'll talk about how to represent vectors numerically, which is what we're going to do in problems. But you need to understand both of these two things. You need to be able to visually picture what vector addition means, and you also need to be able to do calculations. So the first thing we want to be able to do is add two vectors together. So let's say we have this vector and this vector. Okay. So here are the steps for what it means to add two vectors. First, put the tail, this is the tail, the part without an arrow, of one vector at the head of the other. Which one's tail you use and which one's head you use, it doesn't matter. You get the same answer either way. I'll show that in a second. And then second, the resultant, or the answer, the sum, is the arrow pointing from the free tail to the free head. Okay, so let me do it with these two. I'm going to cheat. Is it going to let me? Oh, it doesn't let me do that. Oh. Now I have to draw it like a sucker. Okay, so there's the first one. Now we're going to put the tail of the second one at the head of the first one. And the sum of those two vectors, the resultant, is an arrow with a tail at the free. Okay, so there's two tails, right? There's tails for both of these two vectors. One of them has a head attached to it, and one of them is free. The resultant vector goes from the free tail to the free head. Okay, so that's the resultant. What if you did it in the other order? Well, I told you it doesn't matter, but maybe you don't believe me. So start with that one. Put the tail of the second one at the head of the first one. And the resultant goes from the free tail to the free head. And notice that those two red resultant vectors are the same arrow. They have the same magnitude and the same direction, so they're the same vector. Okay, let me give you an example to do. Okay, so let's say that we have that vector plus that vector. What's the sum? Okay, just take a minute and do that graphically. Okay, so there's two ways you could do this. You could do this one first, the tail of the second one at the head of the first one, and you get that. Or you could start with this one and then put the tail of the horizontal one at the head of the first one, and you get that. And which one of those is right? Well, yeah, it's the same thing. Even though it looks like they start at different places or whatever, we don't care about that. Vectors don't have, they have two properties. Neither of those is a starting point. It's just a direction and a magnitude, and those two are the same vector. Okay? The second calculation you can do is you can multiply vectors by numbers. And numbers are called scalars. And so you can multiply a vector by any scalar, any number. It can be positive or negative. And I'm going to break it up into multiplying by a positive number and multiplying by -1. Because if you want to multiply by -50, you can think of that as multiplying by -1 and then multiplying by +50. Okay. So first, multiply a vector by a positive number. Keeps the direction unchanged. And multiplies the magnitude by that number. So, for example, if you have that vector and you want to multiply it by 3, you get 1, 2, 3. It stays in the same direction but gets 3 times as long. Okay. So the second step is multiplying by -1. Okay, if you were inventing vectors, you just thought of this in your math laboratory, what would you have multiplying by a -1 do to a vector?
Change direction.
Yeah, opposite direction. And that's exactly what it does. So if you multiply a vector by -1, it keeps the magnitude the same. And switches the head and tail. So now it's going in the opposite direction. Okay, so if you have -1 times this vector, what was the head is now the tail, and vice versa. And so you get that. Okay, so let's say that you have this vector, and you multiply it by -2. Geometrically do that calculation. Okay, so this, you have, so the 2 doubles the length, and then the negative means that what was the head is now the tail, and vice versa. Okay? Okay, so there are 2 types of geometric calculations that you're going to need to understand, and we'll spend more time doing this, and we'll spend a lab doing most of a lab doing this. But you need to understand geometrically how vector addition works and how multiplying a vector by a number, by a scalar value works. For most of our calculation, yeah.
Okay, I have a question.
Okay.
So for the -1, is it just like flipping the vector across like the very center of the vector? It's just
Yes. Well, you can think of it as that way. Like I said, vectors don't have any like their location in space doesn't mean anything. The only thing that means something is their magnitude and their direction. But yeah, you could think of it as like, yeah, you could think of it a few different ways because it doesn't matter. It doesn't have to be anchored anywhere. You know what I mean?
okay. So if this isn't anchored anywhere, then it doesn't matter which one you do first. Because if it was
That's right.
flipping,
It doesn't matter which one you do first. That's right. Just like with multiplication of numbers, you know, the order doesn't matter in vector addition or vector multiplication with a scalar. Any other questions? All right.
Just the order you multiply that doesn't matter.
No. So all of that is just like with number multiplication. There are certain kinds of vector multiplication where the order does matter, but we're not talking about those yet. But multiplying by, I mean, you could do, so you could do something like this. Okay, 2 times this, and it follows the same rules of addition and multiplication that you're used to. That's 2 times this plus 2 times this. You could do the multiplication and then do the addition, or you could do the addition in the parentheses and then multiply by 2 and you'd get the same thing. For calculations, we usually won't deal with vectors geometrically. Instead, we'll usually express vectors as components. Components in a chosen coordinate system. And I'm going to talk about coordinate systems a lot, so I'm going to abbreviate those CS. So here's the idea of expressing a vector as components. If you have this coordinate system, so this is the x-axis, this is the y-axis, that's the negative x and negative y-axis. And this is your vector. The components, you can think of this as this vector as the sum of two vectors, one that's parallel to x and one that's parallel to y. So it's the sum of this vector plus this vector, and these two are perpendicular. So if this is the vector v, we'll call this component the x component, and this component the y component. And you can write this two different ways. So this is written that the vector v is equal to the x component times that I says that it's in the direction of the x-axis, plus the y component times the basically times the direction in the positive y, the positive y direction. So this is the positive x direction. This represents the positive y direction. Or another way that I'll write it a lot of times is I'll just give it as coordinates written with the x component written on top and the y component written on the bottom in square brackets. So Vx, Vy, square brackets. Okay? And so what we're going to do next time is we'll talk about first how to come up with these components for a given vector. And then second, we'll talk about how to do calculations using components mathematically. So we'll talk about adding vectors, multiplying vectors by numbers when you have it in terms of components instead of just as a geometric thing. Okay? Okay, let's stop there for the day.